Hello, and welcome back to Introduction to Genetics and Evolution. In the previous video, we talked about the effects of genetic drift over a single generation. I emphasized the point that in small populations, genetic drift can have large changes in allele frequency. I also emphasized that in a single generation, you cannot predict whether genetic drift is more likely to make the allele frequency go up or go down. What we'll do in this video is talk about what happens with genetic drift over many generations, and also look at the interaction between genetic drift and natural selection just a bit. Now again, in terms of this long-term effects of genetic drift, you saw this graph in the last video. If we start with a variable population that has two alleles, the x-axis here is generations, so this is going out 100 generations. The y-axis is allele frequency. We're starting 8 different populations with an allele frequency of 0.5. So big A has a frequency of 0.5, little a has a frequency of 0.5. What you notice is that after many, many generations, if we extended this out, not 100 generations, but thousands of generations, the allele frequency of A, big A, in each population will either be 0 or 1. So we're not going to have any variation left. That basically what's going to happen is basically the whole population will be big A, or the whole population will be little a for every one of these populations. The reason is that once you get to an allele frequency of 0 or 1, there's no variation. One allele is just gone. If the allele is gone, you can't drift back down. You need a new mutation to come in to reintroduce it. But just working with the variation that's present, genetic drift cannot have any further change. So the long-term effects of genetic drift are to remove variation from a population. Now let me ask you this question. I said in one generation we cannot predict whether an allele frequency will go up or go down. Well, let's imagine we start a variable population, all right? So it has big A's and little a's. There's two alleles there. Now let's say the starting allele frequency of big A is 0.6, of little a is 0.4. Okay? What do we expect after a very long period of time? If we were to wait thousands of generations, do we think the population is more likely to be fixed for big A or more likely to be fixed for little a? Which one will go to 100%? Will everybody be big A, or will everybody be little a? Well, that was a little bit of a trick question for you. Now, I mentioned that in one generation, we cannot predict whether you're more likely to go towards more big A or less big A. But what's happening here is we're looking at the effects over long times. And there's an analogy we can draw to this. Imagine a blindfolded person walking aimlessly around. If you start right in the middle, and let's say, for example, this person can only go left or right, and they just take randomly steps this way or steps that way, sometimes bigger steps, sometimes littler steps. If you start right in the middle, you're about equally likely to run into this as you are to run into this, right? Okay, well, let's change this a little. Instead of having this person start dead center, as we start the person over here, where they're about 3/4 of the way over to one side. Are they more likely to eventually run into this, or more likely to eventually run into this? Even if they're stepping at random, since this is closer, they're actually eventually more likely to run into this than they are to run all the way out here into that, if they're just moving around aimlessly. Not convinced? Well, how about this one? Let's say you start right there, and they're taking random steps in 2 different directions. Well, they're pretty likely to run into this end over here, whereas they're very unlikely to run into this end way over there. So this is a funny thing about genetic drift. Now, the probability of a long-term outcome is actually somewhat predictable. So even though in one generation there's a roughly equally likely for an allele to go up or down in frequency, that the frequency of big A may go up, may go down, the long-term loss or fixation of allele is actually more predictable. That again, if you start dead center, you're about equally likely to hit either of the 2 ends. Think of that blindfolded person. If the frequency is much less than 0.5, then it's likely for the allele to be lost. You're likely to run into that 0 end. If it's much greater than 0.5, you're more likely for that allele to be fixed. Well, there's a very simple relationship you might have already anticipated. The probability of eventual fixation, and again, this is over the long term, not one generation. Probability of eventual fixation of allele big A will equal the allele frequency of big A. So if your allele frequency is 0.9, your probability of hitting that 1.0 end is 90%. Your probability of hitting the 0.0 end is 10%, or 1 minus your allele frequency. So let's look at this. Here's 4 sample runs of that program I showed you before, allele A1. Our starting allele frequency is 0.75. So you're towards this end of the overall cage. Again, 3 out of 4 times it's bebopping around there. 3 out of 4 times it ends up hitting 100%. 1 out of 4 times it actually bebops far enough down that it hits 0%. I actually didn't manipulate the data. I actually just ran this as the same do 4 sample runs, and this is actually what it came out with. So as you can see, this probability of eventual fixation is equal to the allele frequency. Now notice there is still some chance the allele will be lost, even if it starts off very abundant. You see this happen in this case. Even though it started at 75%, it bebopped around, and after a few sudden losses, it did actually go to 0. So this does happen, but this frequency tells you the probability of it. Now let's turn this around a little bit. Let's think of it in the context of species versus population. Everything we've looked at so far has been thinking of what's happening in one population and focusing just on that. Now what happens if we're looking at a whole species that has many isolated populations? So let's imagine we're looking at, for example, the Galapagos land snail, which is found on various of the Galapagos Islands. Well, here's a thought question for you. If there are 4 populations of Galapagos land snails, and each individual population is started with an allele frequency of 0.75, what would the allele frequencies be in the populations many years later? Well, you probably can guess that some are going to fix, some are going to be lost, and in fact 75% of them will fix, right? 25% will be lost. So if it's 4 populations, we expect on average 3 to be fixed, 1 to be lost. The second one is something I want you to actually answer here in an in-video question. What would the average allele frequency across all populations be many years later? Let's imagine the 4 populations had approximately the average size. They eventually do their thing. Some are fixed, some are lost. In the species as a whole, so averaging what's happened in each of the 4 isolated populations, there's no migration between the populations or from anywhere else. What will the average allele frequency of big A be? Well, I hope that wasn't too difficult. So, well, again, this is the pattern that we expect to have happened. So some of these allele frequencies will be bopped around. So let's say, for example, here are the 4 islands. Island 1, Island 2, Island 3, and Island 4. Okay. We see in 3 out of the 4 islands, Islands 1, 2, and 4, the allele big A is fixed, which means everybody on that island is big A, big A. And 1 island, little a is fixed. So everybody on this island is little a, little a. So these ones are all big A, big A. That one's all little a, little a. What is the allele frequency across the species as a whole? Well, in this case, we're saying that all of these islands have the same average population size. What we have is 1 island of all big A, big A's, 1 of all big A, big A's, 1 of all big A, big A's, 1 of all little a, little A's. So the species as a whole, even though each individual population has no variation, the species as a whole still has some variation, right? Because the species has some islands that are all big A, and some islands that are little a. And in fact, in the species as a whole, the allele frequency is still 0.75. So it actually hasn't changed in the species as a whole when you've isolated off these islands. So some points to remember is that drift eventually leads to allele fixation or loss in every individual population. Very important facet to it. Now again, the starting allele frequency, or P of big A, is the long-term probability of that allele's fixation. Conversely, 1 minus that should be the long-term probability that allele is lost. But if you have a species with many isolated populations, even though you're going to have some populations fixed for big A, some fixed for little a, the overall species still retains variation with the same P of big A, with that same starting allele frequency. That's a very interesting little facet. Now I want to go into something a little bit related here. What happens when we look at the interaction between natural selection and genetic drift? And specifically, can genetic drift make alleles that are bad spread or even become fixed? Okay, so this is the interaction between drift and selection. Well, this is going to depend on the population size. If the population size is very small, which in that case, again, when the population size is small, those are the times when drift is strong, then genetic drift can sometimes counteract weak selection to make bad alleles spread and potentially even go to 100%. Now, it won't always do it, because remember, drift is a random force, right? That'll sometimes make alleles go up in frequency, sometimes make them go down. And so drift is actually random, but it may cause bad alleles to fix, but it may also push in the same direction as selection. So imagine selection is this constant force pushing down. Let's say it's a bad mutation. Selection is a constant force pushing the allele frequency down. Drift, if it's strong, will be a random force, sometimes pushing it up, sometimes pushing it down. Well, let's look at what happens when you have strong drift and weak selection. What I've modeled here are 6 simulations. This is using allele A1, What I did is I said that the fitness of the big A genotype is 0.98, whereas the fitness of big A and little a is 1.0. So selection is trying to eliminate the big A allele, and it's doing so kind of slowly. Population size here is 100, so it's not a very big population. This is kind of a small population. This would be a case where selection is kind of weak. There's only a 2% reduction in fitness to just the homozygote, so this is a recessive detrimental. There's a 2% reduction in fitness to just the homozygote, but we have very strong genetic drift. So our starting allele frequency is 0.5. What I did is I started 6 populations this way. We see this first one, it bebops around, but eventually big A is lost, as you expect from selection. Here, it bebops a lot more, eventually big A is lost. Bebops some, big A is lost, bebops some, big A is lost. It was a funny one. 1 out of 6 of these actually had a bebop up to the point that everybody's big A. So you've actually lost the better allele. Little a is the better allele. But in this case, you've fixed the big A type. That's kind of funny. And here we've lost big A. So this is a case where genetic drift actually overpowered selection. In some cases here, this one right here probably is a case where genetic drift actually made selection faster. Because you notice that there's a fairly rapid drop. Here, genetic drift slowed it down, and here, genetic drift actually went in opposition. So drift just kind of comes in and monkeys with what selection's trying to do. Now, what would happen, this is a case of fairly strong drift, what would happen if the population size wasn't 100, but was 1,000, meaning there's a lot less genetic drift? In this case, we see a fairly consistent pattern that pretty consistently the allele frequency of big A is going down, going down, going down, going down, going down, going down. We see a little bit more noise in the system than if it was from selection alone, but there's a very consistent trajectory, and we assume if we extrapolate out further, in all 6 populations, the allele will be lost. This is a case where the drift is weak and selection is also fairly weak, but drift is much weaker than selection, that it's not monkeying what selection is trying to do. Now, there are some extreme cases of genetic drift. One example of these is what's referred to as founder effects. This is a strong example of genetic drift when a new population is established by a very small number of individuals from a larger population. They're often non-representative of that original population. You see this often in the case of colonizing islands, and this can cause the spread or even fixation of detrimental alleles. So imagine you have this population here with red squares and blue circles. And if we randomly take 5 individuals, every now and then we'll get an all-blue population or an all-red population. These are non-representative of the original population, whereas this one right here is fairly representative. Now, this has been observed several times in humans. Here are some examples of diseases or traits that are common in certain populations because of past founder effects. So polydactyly, or having that 6th digit, is common in the Amish. Tay-Sachs disease is actually very common in Ashkenazi Jews. So people like Leonard Bernstein, the famous American composer, Albert Einstein, and Sigmund Freud are some examples of Ashkenazi Jews. Interestingly, the Ashkenazi have maternal ancestry traces back to just 4 women. Right? So this is for about half the Ashkenazi out there. They have their maternal ancestry tracing back to just 4 women. So this was a very strong founder effect associated with them. Huntington's disease is interestingly very abundant in Mauritius. It's thought that one of the original founders was either had the disease or was heterozygous for it. And red hair is supposed to be common among the Irish as a result of it. So just to wrap up, some points to remember: in small populations, genetic drift can sometimes overpower weak selection. So remember, genetic drift is random in direction. So if you have strong drift and weak selection, you can actually spread or fix bad alleles because of genetic drift. And founder effects are this interesting special case of genetic drift. I hope that was interesting. Thank you for joining us.